In this lesson, we are going to discover what is meant by kinetic energy, learn its equation, and how to solve problems using it. Have a look at the picture of the car. The car is clearly moving, and it's moving with a particular speed v. So we say that it has movement energy, or to use the technical expression, kinetic energy. So in this lesson, we're going to discover the equation for kinetic energy and use it to solve some problems. So to do this, we're going to imagine an experiment where we have a model car rolling down a slope. Few assumptions we need to make first. We're going to keep our numbers easy here. So we're going to approximate G, which is of course 9.8 newtons per kilogram, to 10 newtons per kilogram. That just keeps the calculations a little bit simpler. We're going to make the mass of our car 1 kilogram, again to keep calculations easy, and we're going to assume there's no friction. So we're going to let this car roll down the slope. There is no engine involved. It's simply rolling under gravity. So we'll begin with the car at point A on the slope, as you can see. The height, the vertical height above the floor at this point is 1 meter, we imagine. This is quite a big slope. So our 1 kilogram car then is allowed to roll down from a height of 1 meter, and it reaches the end of the slope at O. I'm sure you would agree that at the point of release at point A, the car has a potential energy mgh, which is 1 kilogram times our approximate g of 10 times a height of 1 meter, giving it 10 joules of gravitational potential energy. So that's a nice easy number. So we let the car go, and it rolls down the slope, and when it reaches O, it's moving with a certain speed v. More about that shortly. So we measure that speed v. We would need to do that with some sort of iPad and interface. So we'll assume it's a smart car. We then move the car up to position B, and position B is 2 meters vertically above the ground. That's a higher position. Well, how much gravitational potential energy would the car have here? mgh again, this time 20 joules. So it's got greater gravitational potential energy when released from B. We then let it roll down the slope again, and by the time it reaches the bottom of the slope at O, it will have a particular speed v. I hope it's obvious that the speed v in the second case, when released from the higher position, will be a greater speed than it would be from position A. Finally, we take the car up to a final height of 3 meters at position C and release it. Well, up at position C, it's got an mgh there of 30 joules. So when we release it from position C, it's going to roll down the slope and be going even faster when it reaches the bottom of the slope. So, a few observations. I hope it's obvious that the greater the vertical height of release h, the greater the gravitational potential energy EP, which equals mgh. Remember, m is constant at 1 kilogram, g is constant at approximately 10, so the bigger the h, the bigger the EP. Okay, so let's imagine we did some measurements on the car, and what we did was we measured the original gravitational potential energy EP. That's quite easy, we just do an mgh calculation, 10 joules, 20 joules, 30 joules, etc. And we'll plot that along an x-axis. So if you look at the axes on the left of the diagram, you can see EP lost. Of course, all the gravitational potential energy lost becomes kinetic energy gained. So as the car runs down the slope, the gravitational potential energy lost becomes kinetic energy gained. So those two are equivalent as a number of joules. On the y-axis, let's imagine we measured V using our smart car technology and Bluetooth with the iPad, etc. We're going to measure the final speed of the car. Now I think you can tell that the greater the original potential energy, the greater the speed. But when we plot a graph of the potential energy lost or the kinetic energy gained against speed, it's not a straight line. We get a curved line like this. So clearly the speed does get greater when you release from a higher point, but it doesn't go up in a nice, linear, smooth, straight line kind of way. So what we do is we replot the graph, but this time we don't plot the speed on the y-axis, we plot the speed squared. And when we plot the speed squared, we do get a nice straight line. And we always like straight lines in physics because they're much easier to deal with mathematically and to help form an equation with. Let me emphasize that we're plotting here speed squared. So here we have our graph, v squared on the y-axis, and on the x-axis we have our kinetic energy. Remember, all of that kinetic energy comes from the gravitational potential energy, but I'm simply labeling it EK here, kinetic energy in joules. So it's a nice straight line graph. In mathematics, this graph would have the equation y equals mx, where m is the constant gradient of the line. So bear that in mind as we do a little bit of analysis. Well, from this graph, we can say that the kinetic energy is directly proportional to the speed squared. That is the kind of direct proportion relationship which always applies to straight line graphs. You can think of direct proportion as meaning that if you double one quantity, you double the other. If you triple one quantity, you triple the other. Okay, in symbols, we can write EK is directly proportional to V squared. That little symbol in between the EK and the V squared just means direct proportion. Now mathematically, if one quantity is directly proportional to another, we can write it as an equation. And the equation is that EK then is a constant times V squared. That constant is the constant of proportionality. It's also the gradient of the line. But physically, what does it mean? Well, you can't tell what it means physically here unless you do an experiment. And when we do experiments, we find that the constant turns out to be half the mass of the body, in this case the car, a half m. That's the thing that didn't change, it's a constant. So having discovered the constant is a half m, when we insert that into our equation, we get that the kinetic energy is a half m v squared. This is a very important equation. You will use it quite a lot in mechanics, and it's on the equation list. Remember, the mass must be in kilograms, the speed must be in meters per second, and that will give you your kinetic energy in joules. One final point, all energy is scalar, so kinetic energy is no exception. It is also a scalar quantity. Right, let's do a worked example. Ben is a fast runner. If his mass is 74 kilograms and he runs at a speed of 7 meters per second, find his kinetic energy. Right, what I'd like you to do is to pause the video at this point, take a pen, calculator and some paper, work out the answer using the equation, and then resume the video to see the solution. So pause the video now. We begin by listing the variables as always. Kinetic energy EK is the unknown, mass is 74 kilograms, and the speed is 7 meters per second. We then state the equation, substitute in our values, so half mv squared is a half times a mass of 74 times 7 squared. Now, important observation at this point, do not forget to square the v. That is such a common mistake, and you'll lose marks immediately if you do. So remember to square the V. When you do square the V, you get 49, and Ben's kinetic energy then is 1,813 joules.